This section is about the characteristic equation, which is used to find the eigenvalues. So just as a little review from the determinants, we know that a matrix is invertible if and only if the determinant is not 0. We also know that the product of the determinants is the determinant of the product. We know the determinant of the transpose is the same as the original. We know if a matrix is triangular, then the determinant is the product of the entries on the main diagonal. And then we saw how row reduction affects the determinant. So if we swap rows, it changes it by a negative sign. If we multiply a row by a constant, it changes the determinant by that same constant. If you add a multiple of a different row, then it does not change the determinant. We also looked at this equation and showed how it was equivalent to this one. I'm just going to do it another way. So we have ax equals lambda x, but x is the same as the identity times x. So if you multiply by the identity, it doesn't change the vector. And then I'm going to subtract over. So I have ax minus lambda ix equals 0. I'm going to factor out on the right. So I have a minus lambda I times x equals 0. So those are the same. The eigenvalues of a are the values of lambda that make the determinant of a minus lambda I equal to 0. You may also see determinant of lambda I minus a equals 0. Either one works. And the determinant of a minus lambda I is the characteristic polynomial. Notice there's no equal to, so the polynomial does not have an equal to, but the characteristic equation just has that equal to 0 part. So if we have a quadratic characteristic polynomial, then we can solve for our lambdas using the quadratic formula. So we're going to practice that. Exercise 1 wants us to find the characteristic polynomial and the eigenvalues for the matrix. So the characteristic polynomial is determinant of a minus lambda I. A minus lambda I is this a, and then lambda I is the identity matrix multiplied by lambda, so we have lambdas on the diagonal. So then if we subtract those two, we'd have 7 minus lambda, negative 2, 2, 3 minus lambda. So the determinant of 7 minus lambda, negative 2, 2, 3 minus lambda is AD minus BC. So when I multiply these two, I'll have that middle term. So I'll have 21 minus 3 lambda minus 7 lambda plus lambda squared plus 4. Just rearranging and combining like terms, I have lambda squared minus 10 lambda plus 25. So that is my characteristic polynomial. To find the eigenvalues that correspond to that, I'm going to solve this characteristic equation. Factoring, I get x minus 5 times x minus 5. So I get that lambda equals 5. I'm just going to say now that because 5 is a double root, it has multiplicity 2. All right, so for those of you that may have had differential equations, you often do this a different way. You may see the trace determinant plane. So I'm just going to do this differently, and this only works for 2x2s. So I'm going to erase and do it again. Okay, the trace is the sum of diagonal entries. So here it would be 7 plus 3, which is 10. And the determinant of the matrix is 21 plus 4, which is 25. And the characteristic polynomial would be lambda squared minus the trace of a times lambda plus the determinant of a. So the characteristic polynomial for a 2 by 2 is this, so which is lambda squared minus 10 lambda plus 25. So for a 2 by 2, this is pretty quick and easy. The other method works for all sizes. So a minus lambda I is the determinant of, when we subtract off lambda from the diagonal, 10 minus lambda, negative 6, negative 8, 6 minus lambda, which is 10 minus lambda times 6 minus lambda minus 48. So I get 60 minus 16 lambda plus lambda squared minus 48, which is lambda squared minus 16 lambda plus 12. And then if I think about the trace is 16, and the determinant is 60 minus 48, or 12. And I get lambda squared minus 16 lambda plus 12. So those are the same. To find the eigenvalues, I want to set this equal to 0. So lambda minus 16 lambda plus 12 equals 0. This is not factorable, so let's use quadratic. So lambda equals negative b plus or minus b squared minus 4ac all over 2a. So I have 16 plus or minus the square root of 208 over 2. And you could simplify this. So notice I have two distinct roots. I have 8 plus root 52 and 8 minus root 52. I also want to notice that those are both real numbers. In this next one, so let's do the trace is 9, and the determinant is 20 minus negative 12, so 32. So I'll have lambda squared minus 9 lambda plus 32. That's my characteristic polynomial. To solve for the eigenvalues, we'll set it equal to 0. So lambda equals negative b plus or minus square root of b squared minus 4ac all over 2a. So I have 9 plus or minus 81 minus 4 times 32, square root of negative 47 all over 2. The negative on the square root means this is 9 plus or minus I square root of 47 over 2, keeping in mind that I is equal to the square root of negative 1. So these are complex roots. In exercise 2, we are asked to find the characteristic polynomial. I cannot use that trace determinant thing here. There is another modification of that that you can look up if you want. So determinant of a minus lambda I would be determinant of negative 1 minus lambda 2, 2, 2, 2 minus lambda, negative 1, 2, negative 1, 2 minus lambda. Combining the bottom ones, so I have negative 1 minus lambda times 2 minus lambda times 2 minus lambda plus the 2 times negative 1 times 2, which is negative 4, plus negative 4 again. And then I'm going to subtract off the top ones. So I have 4 times 2 minus lambda plus negative 1 minus lambda plus 4 times 2 minus lambda. I'm going to do some algebra. So here's the characteristic polynomial. You could also have lambda cubed minus 3 lambda squared minus 9 lambda plus 27 as your characteristic polynomial. When you multiply it by negative 1, it's not going to change when you solve for it equals 0. I realize it did not ask us to find the eigenvalues, but we're going to do it just to refresh your memory on how you might factor this. So if we're trying to solve lambda cubed minus 3 lambda squared minus 9 lambda plus 27 equals 0, this is factor by grouping, so I can take out a lambda squared, and I'm left with lambda minus 3. And on this last two terms, I can factor out a 9, a negative 9, and I'm left with lambda minus 3. And now in these two terms, there's a common lambda minus 3, and I'm left with a lambda squared minus 9. And I'll have lambda minus 3 times lambda minus 3 times lambda plus 3. So my eigenvalues are 3, and here it's a multiplicity of 2, and lambda equal negative 3. So the nice thing about diagonal matrices is that the eigenvalues are on the diagonal. So if you are given a triangular matrix or a diagonal one, here are the eigenvalues. So my eigenvalues are lambda equals negative 1, lambda equal 2, and lambda equals 7. Negative 2 has a multiplicity of 1, 2 has a multiplicity of 2, and 7 has a multiplicity of 1. This last little part is on similar matrices. We say that two matrices are similar if there's an invertible matrix P such that A equals PB P inverse. So if two matrices are similar, then they will have the same characteristic polynomial and also the same eigenvalues with the same multiplicities. So just to point out, the converse is not true, and converse means is the if then is swapped. If they have the same characteristic polynomial, they may or may not be similar. And just as a reminder, similarity is not the same as row equivalence, because row operations on matrices usually change those eigenvalues. So I want to know, given A, B, and P, are these similar? So is it true that A is P, B, P inverse? So P inverse would be 1 over the determinant, so negative 1 minus 1, and then you swap those and negate those. So if we multiply, we can multiply these two first, then these two. We will get which is equal to A. So check, they are similar. So by inspection, how do we find the eigenvalues of A? So knowing that A is similar to B and B is diagonal, the eigenvalues of B are 2 and negative 1. So the eigenvalues of A are also 2 and negative 1.